All right, so this is 30-2, lesson 2, equivalent forms of rational expressions. And again, a rational number is like 10 over 15. What we can do to make that is I can just go, okay, well, I can divide out 5 from both of those things. Now, we don't even really do this step anymore, but we technically did. So you go, okay, that's 2/3. So I found my common factor and then factored it out. We can also make it bigger. I can go, oh, wait a sec. Instead of 10/15ths, I could make this 20/30ths. And all I'm doing there is going 10 over 15, and let's multiply by 2 on the top and the bottom. As long as I'm multiplying by the same number on the top and the bottom, this is really 1, right? I've multiplied my thing by 1, and that's why it's an equivalent form. I call that a special 1. It's 1, it just looks different. So that's what we did to work through there. So 18 and 42, my common factor between 18 and 42 is, I don't know, 3, I think. 6 goes into both. So I can divide both by 6. 18 divided by 6 is 3. 42 divided by 6 is 7, so that's 3/7. Or I can multiply it. Let's multiply by 2. 18 times 2 is going to be 36. 42 times 2 is going to be 84, so I could go to 36/84ths. Or I can factor it. So 18 is really 2 times 3 times 3. You could do that with a factor tree like this. 2 times 9, sorry, and then 9 breaks into 3 by 3. 42 is 2 by 21, which is 3 by 7. So this is 2 by 3 by 7. And now I can just cancel out. Boop, boop, boop. And so 3/7 is my final answer. Now, the same thing is basically true. We're going to look at these two pieces here. Here I have two different rational expressions. If I put in 2 times, or put in 1 here, sorry. 2 times 1 is 2. 1 squared is 1. 2 times 1 is 2. So that's going to be 3 in my denominator and 2 in my numerator. This one is also 2 over 3. 2 times 2 is 4. 2 squared is 4, and 2 is 4. So this is going to be 4 over 8. But that's the same as 1/2. If I put it in here, this is just 2 over 4. Which is the same as 1/2. If I put in 3, 2 times 3 is 6. Bottom is 3 squared is 9, plus 6 is 15. So 6/15ths, which is then going to be 2/5. If I put in 3 here, 2 is my numerator and 5 is my denominator right away. If I put in 4, 2 times 4 is 8, over 4 squared is 16. 2 times 4 is 8. 16 plus 8 is 24, so it's going to be 8 over 24, which is, I think, just 1/3, if that makes sense. Let's try it over here. Here I get 2 over 6, which is definitely 1/3. So that leads me to believe I probably did this one right. Because what we can see is that all of these are exactly the same at all the values we tried. Doesn't mean they'll be the same at all the other values, all the values that we tried. So when x is replaced by 1, 2, 3, or 4, these things are exactly the same, which means they're what we call equivalent forms. They're not equal to each other, but they are equivalent forms. If we were to do this and see how they could be equivalent forms, my 2x one, I could factor out my common factor and then have x plus 2. And now I can see that the x here and the x here can cancel off, so that just becomes 2 over x plus 2. So we can reduce these things to simplest form. Now the one thing we've got to be careful of is that before we cancel, we need to include my non-permissible values, my limitations or restrictions. So we divide out factors, not terms. Not terms. What I can't do, and this is what people are really tempted to do, just go, hey, 2x over 2x. Cool, it worked. Not true. Not true. Don't do it. It's not a pretty picture. Okay, so again, this is key. To reduce fractions, We divide up factors, not terms. So, non-permissible values, though. If we try this one, 0 can't be in the denominator. If we put in 0 here, this is just 1. If we put in -1, that's fine. What's that going to be? Just +2. We're going to get -2 over -1, which is +2. We get 2 here. If we put in -2, we get it does not exist in both cases, because both denominators are negative. If we put in a -3, what am I going to get? -2, I think. 2 times -3 is -6. -6 divided by -3 squared is +9. 2 times -3 is -6. -6 times, or plus a +9 is +3. Thinking. -6 over +3 is -2. Oh, look. I almost know what's going on. That's the same thing. So this one is not defined at 0 and 2, -2. This one's not defined just at -2. So they don't match. Anyway, these values make it non-permissible because you cannot divide by 0. Okay? And then we talk about those as being non-permissible values. When we write the equivalent forms, we just include the old non-permissible values. So the non-permissible values stay with the rational expression, even when the factor that created the non-permissible is gone. Right? If you were just to look at this, you would think 0 is okay. But we know it's not because we remember the original form. This is kind of like the expression, what happens in Vegas stays in Vegas. This is what happens in the rational expression stays in the rational expression. No matter what else we do to it, non-permissible value stays. Equivalent form of this. So I could say, well, I could divide everything by 2. If I divide everything by 2, that's going to give me 4x over 3x minus 2. That works. Multiply. Let's multiply everything by 2 because it's easy. 16x over 12x minus 8. Multiplied everything by 2. Now, factoring out. What I'm going to do is look at a common factor in my denominator. Actually, I'm going to break apart my numerator too. 8 is the same as 2 times 2 times 2, and then I still have my x. In my denominator, I can take out a 2, and this is going to give me 3x minus 2. And now I can see that I can hack off a 2 from both of these. Now I'm going to reconstitute it, multiply it all back together. It's going to make 4x in my numerator and 3x minus 2 in my denominator. Note that I couldn't go, hey, 2 and 2. That just doesn't work. It has to be all the way factored out for me to cancel it. It must be a factor, not a term. Which of the following are equivalent to this? Well, we have to check all of them. So let's try and simplify them all. This one's already in simplest terms, so if we simplify them and they work, then we should be good. This I can divide, nope, nothing comes out because nothing can factor out here. No common factors. When we see a negative in front of the x, it's a really good strategy to make the x positive by taking a -1 out. In this case, I also have a common factor of 3, so I'm going to take out a -3 here, and that's going to leave me with -1 plus 2x, or I could rewrite that as -18 over -3 times 2x minus 1. And again, we generally want to put our x term first to make sure we're actually comparing the same things together. So this part looks the same. That's a good sign. Now I just need to simplify these. 18 divided by 3, well that's 6, and the fact they're both negative makes it positive 6. Hey, so this one works. This is equivalent. This is not equivalent. If I'm not sure if something is equivalent or not, I could try a value. Let's put in 1. This would be 12 over 4 minus 1. 4 minus 1 is 3. 12 over 3 is 3. No, 12 over 3 is 4. So if you put in x equals 1, this thing has a value of 4. If I put in x equals 1 into this, 2 times 1 minus 1 is just 1, and that gives me 6. 6 is not the same as 4, so it didn't work. This case, I'm going to take out some common factors. This is going to be 2 by 3 by x is my whole breakdown of my numerator. And take out x out of here, this leaves me with 2x minus 1. This x and that x can cancel, so now I have 6x over 2x minus 1. That doesn't work. Not the same. Too many x's in the numerator. Close, but not close enough. This is where we've got to be sometimes a little careful. If I put in 1, I get 6 here and 6 here. I'm like, hey, it worked. Awesome. Put in a second value just to be sure. If I put in 2, this is going to be 6 divided by 2 times 2 is 4, minus 1 is 3. 6 divided by 3 is 2. So if x equals 2, this thing is 2. If x equals 1, with an expression of 6. So this worked for the first one. If you put in 1, you get 6. But if we put in 2, we get 12 over 3, which is 4. So it doesn't work on closer analysis. This one also doesn't. So the only one that works is number 2. Again, these look similar, right? If you put in x equals 0, you're like, hey, 4 over 2, that's 2, and 8 over 4, that's also 2. But it's not necessarily true. Need to check. Now, technically, you need to check all possible values. We can do it algebraically to check all those values at the same time. But we can just look at it right away and spot one. All we need to do is find one value that makes it not true, and that's enough to disprove his conclusion. I'm going to put in x equals 2. 4 over 2 minus 2, well, that's 4 over 0. That's undefined, or does not exist. If we try this, well, hey, 4 minus 2 is just 2. 8 over 2 is 4. This works. But 4 is not the same as undefined, therefore not equivalent. All right, hopefully that makes sense. That's a good